everybody. Today we're going to take a look at chemistry and biology. I know that kind of sounds a little bit weird, but in fact in high school you probably had them as separate classes. But to be honest, you can't really learn about biology without knowing something a little bit about chemistry. Chemistry is considered the central science, and it's kind of in the middle of, you have biology and the life sciences, you have physics and the physical sciences, and it's somewhere in between, and that's why it's called the central science. But if you take a look at biology on the most basic levels, what you'll find there is chemicals. So that's where we're going to be today, talking about the chemistry of biology. Let's go ahead and get started. Okay, so we couldn't talk about chemistry without addressing the fact that the simplest particle of all matter is the atom. There's no doubt that in biology, the simplest form of structure in biology is the cell, but an atom is much, much smaller. An atom is the simplest particle of anything, of stuff, including cells. So within cells, you probably have billions and billions of atoms as well, just to give you an idea of the scale of size there. So here we have an artist rendering of a cell, and we can take a look, and hopefully some of these things seem familiar to you. We see the yellow spheres, and they represent what we call protons, and they're found in the nucleus. Orange spheres are the neutrons. You notice that there's no charge designated on them. The small white spheres, which you see on the outside here, kind of in a ring-like form, those are our electrons. So then what we could say, the nucleus, the centermost part of our atom here, is contained of two things. It's protons and neutrons. They're also densely packed together, so it's a very, very small, dense center core of every atom. And therefore, the area outside the nucleus, all of the space outside of that small, densely packed central area, will contain your electrons. We can also talk about them in terms of charge that they carry. Protons, you can see the plus on them. They have a positive charge, and electrons have a negative charge. Neutrons have no charge. They are considered neutral. So there is one part of this picture up here, let me go back to that just for a second, that is grossly out of scale, and that is the nucleus. So this artist here drew this picture so it would be easy to understand in terms of counting up the number of protons that you see here. I see 1, 2, 3, 4 in the back, 5, 6, 7 protons. And on the outside, if I was to count the electrons, I have 1, 2, 3, 4, 5, 6, 7 electrons on the outside. So they did that to help you count particles. Now, what we have to understand is that the nucleus itself is nowhere near this big. In fact, if I was to draw it in, I could probably use just a small little dot right in the center. And that would be more realistic as to how the nucleus size is in relation to the electron field around it. So there's some comparisons made by comparing the size of the nucleus of an atom. If it was, say, the size of a golf ball, and you put it on the 50-yard line of a football field, that the electron clouds that are surrounding that nucleus would go all the way past all the stands and all the bleachers, all the way into the parking lot. I've also heard someone compare it, if you had a beach ball here on planet Earth, that the electron field in the clouds would stretch all the way to the moon. So that gives you an idea of how small the nucleus actually is in comparison to the electron clouds. So the other thing I wanted to mention, you heard me say electron clouds. The artist drew the picture with the electrons in a ring. And it's very easy to understand electrons when they are drawn in a ring, because it seems like they go around in a circle in an orbit. That's kind of what we consider the Bohr model, and it's pretty much outdated at this point, and now we have the quantum model. And the quantum model doesn't have them in circular orbits, but instead, now electrons are found in clouds, like you see here. If we were starting at the nucleus and building clouds outward, the first cloud would be this spherical one right here. Remember, this would be in 3 dimensions. The second cloud would be this spherical one right here. Once you get past a spherical model, we'd then start looking at these dumbbell-shaped clouds that electrons are found in. And we have to get away from the thinking that it's always in a circular orbit like a solar system. It's really not. But also, this is not chemistry class, this is biology. So when the artist draws them in a circular orbit, that will actually help us out a little bit in trying to figure out the number of subatomic particles. I just wanted to say a note about that. Okay. So this is just a table full of information here. The things that we see here will come in handy as we learn biology, like the symbols. We have E with a little minus sign for electron, P with a plus for neutron, and N with a 0 right there, or a Greek letter naught to represent no charge at all. The charge of an electron is 1 minus. The charge of a proton is 1 plus, and a neutron, we said, has no charge. Now, the masses of these subatomic particles, and notice I keep saying subatomic because this term here means smaller than an atom, so subatomic means the things that make up an atom. With the electron, you're going to notice 9.1 times 10 to the negative 28 grams. Now, that number is extremely tiny, okay? You have to go through a lot of zeros after a decimal point to actually hit a digit. But notice the proton and the neutron. They're also very tiny at 1.6 times 10 to the negative 24 for each one. Now, although they're all really tiny, if you look at the negative 24 that you find with the proton and the negative 28, we are talking about a proton that's much, much bigger, even though they're both small. So how much bigger is it? Well, if a proton and neutron have a 1-to-1 ratio in size, the electron size in comparison is about 1/1840th of it. So roughly about 1/2000th of the size of one of those. But for as small as an electron is, it does carry a pretty big punch because its charge is equal and opposite that of a proton. So bottom line is, as we talk about these subatomic particles, if we compare them against each other, a neutron is large with no charge, a proton is large with positive charge, and an electron is very small with a negative charge. And this little red dot gives you the relative size comparison of them. Okay, next thing, now that we've dealt with the atom, where can we find information about atoms and elements? Well, of course, it's the periodic table. And this is just a standard sample box of one of the 118 elements that we have. This one here is for helium. And you'll notice that over the top of an element symbol, we have a number. And that number corresponds with the atomic number, which is the number of protons of an atom. And we can also say it's the number of electrons as well. A little bit later, we'll add a little bit of some special cases to when you can't rely on electron number for the atomic number. Underneath the atomic number, we have a 1, 2, or 3-letter abbreviation for the symbol of a particular element. Usually, the name will be found down here below it as well. So this one here is just kind of a very simplistic periodic table box, but most of them will have the name of the element underneath it. And the names can have many different origins, from words in Latin to locations where elements were found to a number of other European languages where it may have been taken from. One, for example, is the element tungsten, which comes from the German Wolfram. So tungsten's symbol is W, and when you look at it, it's like it makes no sense. To the person who hasn't studied any science, why would it be W? And that's why. And then lastly, underneath each element, you have the atomic mass. And that number is given in AMU, or atomic mass units. Atomic mass, we'll go into its thorough definition a little bit later, but we can think about it as protons and neutrons bearing most of the weight of an atom, and that's where a portion of that number comes from. The rest of that number comes from the fact that elements have different types of themselves, which we'll get to in one of our I words a little bit later, but that will come into play and we'll explain it when we get there. Okay, so to understand chemistry and apply it to biology, there's a few fundamental ideas, and those ideas are going to be found in like vocab terms. So let's go through some. First of all, an element is a substance that cannot be broken down. For our purposes, we're going to assume that the 118 elements on the periodic table are the way they are. And since we're only using the top half of the periodic table for the most part in biology, we'll say that's like the bottommost level. A particle of that bottommost level then would be considered an atom. An atom would have all of the characteristic properties of a given element from the periodic table. And we just went through a slide and we saw all three of these subatomic particles. There's that word again. And we also saw the atomic number, meaning the number of protons and often the number of electrons. And we said that all atoms are neutral, therefore that's why the protons and the electrons are equal. It's only when a particular atom goes non-neutral where we're going to see a different number of electrons. Okay, so here is a very generalized periodic table. And you can break it up in a number of different ways. You can go very basic, or you can get into the names of all the different groups, depending on what your purposes are. But for us right now, we'll take a look at the left-hand side of the periodic table. So basically, we have all this stuff here on the left till about here is all considered metals. And inside of the human body or any living organism, you're not going to have a ton of metals. They're more likely going to be found in trace, which means in very small quantities. And then on the right-hand side of the periodic table, we have nonmetals. And this is where a majority of the substances that make up living things come from. So you can notice the colors here corresponding to the table up here on top. And with the human being, for example, if you wanted to know what are the elements that are found the most in a human being, it would be the top four: oxygen, carbon, hydrogen, and nitrogen, like you see there. And to easily remember it, you can just think of the acronym HONK. Okay, real easy to remember. If you're ever asked to know six, it's gonna go from HONK to let me change colors here so you can see it. CHOMPS. So CHOMPS is the top six elements. You have carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Top four: hydrogen, oxygen, nitrogen, carbon. Okay, so now we are at our first I word, called an isotope. And it's going to be related to something that we have called mass number in chemistry. So we'll kind of try to separate those, differentiate those so they're easy to understand. We could say that all atoms of a given element have the same number of protons and electrons. That fact we've gone through twice now. However, the number of neutrons may vary. We haven't talked about the neutron number yet. So if we take a look at the three isotopes of hydrogen. Hydrogen is our first element, and you can see over here you have one, and let's go ahead and we'll come up with a coding system for these pictures over here. So red is going to equal proton, and then green is going to equal neutrons. There we go. Okay, so I know all three of these are hydrogen. Why? Because each one has one red dot, and the number of protons equals the atomic number. And by looking on the periodic table, number one is hydrogen. But the green represents the number of neutrons hydrogen can have. And in the first picture here, you see that hydrogen has none. And here you see that hydrogen has one, and here you see hydrogen has two. So all three of these forms of hydrogen are considered an isotope. They have the same number of protons, but a different number of neutrons. If we look at our helium example, okay, I know that this is helium because there's 2 protons in this one, and there's 2 protons in that one. That guarantees that I have helium. Now, the neutron number, however, varies. So instead of having 2, this one just has 1. And this one has 2 protons and 2 neutrons. So these two are the isotopes of helium. Now, the other word from the heading is mass number. So mass number is going to be the number of protons plus the number of neutrons. So we can go through for each one of these and we could determine what its mass number is. So for this first isotope here, the mass number would be just 1 because there's just one proton there. For this one, the mass number would be 2. For this one, the mass number would be 3. Helium, this one has a mass number of 3, 2 plus 1, and this is 2 plus 2, so that's 4. Lithium, this version here, 3 protons, 3 neutrons, mass number 6. And this one's also lithium because it has 1, 2, 3 red dots. And it has 4 neutrons, so its mass number would be 7. So protons plus neutrons equals mass number. One thing that teachers love to ask their students is how to determine the number of neutrons where you are given the mass number of an element. For example, if I told you the mass number of carbon, let me throw the number symbol in there, mass number of carbon is 14. Your teacher might ask, how many neutrons does carbon have? So how would you do it? Well, if the mass number is 14, we're just going to go ahead and we're going to subtract the atomic number from it. So 14 minus 6 equals 8. So it would be 8 neutrons. Okay? So, you can use plenty of examples from the periodic table. So whenever you are faced with this type of chemistry, make sure you have a periodic table at the ready, set it right next to you, and you'll be able to do these much, much quicker because you can find the number and quickly do a subtraction problem. Okay. Last thing I wanted to mention is why are we learning this? How are isotopes useful in science? Well, isotopes, a lot of them give off energy. They're unstable. And the ones that are unstable, we tend to use those because we're going to go ahead and detect that energy in our efforts to do something. For example, if someone swallows a radioactive isotope and it's giving off energy, we may be able to follow, using specialized equipment, the energy that's given off by this isotope as it passes through a person's digestive system, because maybe we're looking for some kind of blockage within a digestive system. Maybe we want to see how the blood flows in a person whose circulatory system has been compromised. So we will use an isotope to give off energy, and then we can see it on a scan. Chances are, when you were in biology, you also heard about carbon-14 dating. Carbon-14 gives off a certain amount of energy at a certain rate, and we're able to date old dead things by using that specific isotope. So it's a very handy chemistry tool in biology. Okay, next, how do we write an isotope? Name an isotope and write its symbol. The simplest thing is the standard naming format. So here you see that all you really do is you name the element followed by the mass number with a hyphen in between. So carbon-14 that I just mentioned for those radioactive tests would be written like this: carbon hyphen or dash 14. Here's chlorine-35. The other way that we tend to look at how to write a symbol of an isotope is by way of a nuclear symbol. A nuclear symbol has the mass number over the atomic number followed by that element symbol. So if we were doing carbon-14, we'd have the mass number of 14 over 6 and the element symbol there. Chlorine-35, you would have 35. You have the element symbol, and then you have the atomic number underneath it. Sometimes your teacher might get a little tricky, and instead of giving you both of them, they'll give you just one of them. So like they might go like this. They might go 7 next to the element lithium, and then they might ask you, how many neutrons does lithium have? And if you can remember that past formula, mass number minus atomic number equals the number of neutrons, well, then I know what the atomic number is of lithium because I have a periodic table. I look at it, I find that it's 3, so I can go ahead and write it in myself, and mass number over atomic number, I could just go like this, and that gives me 4 neutrons. So it's actually a lot easier when a teacher tells you to calculate the number of neutrons and they give you the nuclear symbol, because then all you have to do is put a line underneath it and subtract. 35 minus 17 is 18 neutrons, and 14 minus 6 is 8 neutrons. So it's really easy to do when they give you it like that. Okay, so now that we know a little bit more about atoms and isotopes, let's start talking about chemical bonds. A bond is a force that holds atoms together, and there's different types of chemical bonds out there. We'll go through at least 3 of them. So bonds that result from attractions between oppositely charged ions are called ionic compounds. Now, notice that the word atom wasn't used, but it was oppositely charged ions. And what happens here is you're going to have an atom that has the same number of protons and electrons, but that can change. Electrons can be gained and electrons can be lost. And when they are, your particular atom that you're looking at is no longer an atom, it's an ion now. So if chlorine was to gain an electron, it would become the chloride ion. If magnesium lost 2 electrons, it would be the magnesium ion. So when an atom gains or loses electrons, it's no longer an atom, it's then called an ion. Okay, and if we take a look down here at this little mini periodic table, you're going to notice that it's only the left side and the right side that is shown here. And that's just for simplicity. If I went into the central region, it would confuse you more than it would help you for now. So let's just stick with these big groups here, groups 1 and 2, and groups 13 through 18, or 3A through 8A for some periodic tables. All right, so here's the deal. Hydrogen, you notice that this element and all of the elements underneath it in this group here, they all have 1 dot next to them. The dot represents something called a valence electron. A valence electron is electrons that are found on the outermost energy level of a particular atom. So if you're a group 2 element, you have 2 valence electrons in your outer shell. And the outer shell is the one that does all the bonding in chemistry. Looking over on the right hand side of the periodic table, boron has 3, this group here, the carbon group has 4, group 5A has 5, 6, 7, and 8. You max out at 8. And what happens is that in chemistry, 8 is considered full and happy. So your atoms are going to try to acquire 8 electrons in some way. Through some mechanism, whether it's sharing, giving, or taking, they want to become like this group right here. They want 8, what we call an octet of electrons. So what we can say is that atoms from the periodic table have different number of valence electrons. Each group has their own particular number. And in the center of the periodic table, what we're going to find is that these here have multiple charges, or oxidation states, they're often called. Our bottom line is that valence electrons are the ones that deal in bonding. They're found in the outermost shell of an atom, and we can basically know the majority of the ones that are important for biology. Group 1 has 1, group 2 all have 2, group 3A have 3, 4A 4, 5, 6, 7, and 8. And that's going to help us figure some stuff out pretty soon here. Okay, now you notice that on the previous slide we had the metals in group 1 having 1, and the metals in group 2 having 2 electrons each in their outermost shell. And they're trying to get to 8. So there's 2 ways for them to get to 8. And this is where logic kind of comes into play. If I have 2 electrons and I'm trying to get 8, I can go about it 2 ways. I can gain 6 more, or I can lose 2. Now let me show you how that works for a second. Let me go back to this, and I want you to look right here. So beryllium, it has 2, and to be like neon, it could gain 6 more to be happy, or it could lose these 2 on its outside, and that will bring it back to, and helium kind of disappeared here, but helium has 2 electrons, and helium is a stable atom in the noble gas group. Now, that's probably a bad example to use because, like, he just said 8. Why is there 2 stable? Well, if you find yourself in the rightmost column of the periodic table, you're going to be stable. And at the top level, you haven't reached 8 yet. So let me use a different one. Let's say you're calcium. You're this atom right here, and you gain 6 to be like krypton. That's one way you could do it. Or you could lose 2 electrons, and that makes you like argon. So if I strip off the 2 electrons there, now I resemble argon in terms of my electrons. Well, how did I go from 2 to 8? Because if you strip off the outer shell and it goes away, what you uncover is a level of 8 underneath it. Because as you go left to right, top to bottom on the periodic table, you're building up these electron orbital shells, these orbital clouds we were talking about earlier. So that's the mechanism of what happens. Now imagine that you are bromine right here. You have 7 valence electrons. There's 2 ways you can get 8. You can gain 1 and be like krypton, or you could lose 7 to be like argon. Because if you strip off 7 of these, then I'll have argon's number of electrons. Okay? So that's how that works. If you think about it in terms of numbers, neon is atomic number 10. That makes sodium 11, and that makes magnesium 12. Okay? So if I have 12 protons, let's just say I have 12 electrons as well because I'm magnesium. So if I lose 2 electrons to be like neon, then I have 12 minus 2, and that gives me 10 electrons, which is, of course, neon's atomic number, and I'd be like neon in terms of my electrons. However, I am still going to be magnesium because what really matters is my number of protons. 12 protons is always magnesium, regardless of the number of electrons I have. So I have 12 P's, I have 10 E's, so overall I have 2 more positive charges than I have negative charges. And that's another reason why magnesium ion is the magnesium 2 plus ion. Because if I have 12 positive P's and I have 10 negative E's, I'm netting 2 positive, and that's where the ion charge comes from. Okay, so we said metals tend to lose electrons, nonmetals are going to tend to gain electrons, and they do that in effort to be like, the most stable group on the periodic table, which is going to be, of course, the noble gases, or group 18 or 8A. Let's go over some bottom line facts. The atom forming the ions does not change identity. It just resembles a noble gas in terms of its electrons. It still remains the same element, like I was saying with that magnesium example. So if chlorine gains an electron to resemble argon, it's still chlorine, just a chloride ion. So chlorine was atomic number 17. If it gets another electron instead of 17 electrons, it has 18. So it has 1 more negative charge now than it has positive charge. So chlorine is going to be the chloride ion, and it's going to have a 1 minus charge, and most people just write the negative for 1. You don't have to put the 1 in, but you can. All of these atoms want to be like the noble gases, group 18 elements. Okay, now the ionic bond forms when 2 fitting partners find one another. Now, here's what I mean by fitting partners. Okay, so sodium is a group 1 element, so it has 1 valence electron. Chlorine is a group 17 element, so it has 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, each one of these atoms is on a mission to become stable. They both want 8 in their outer shells. So what's going to happen here is sodium, being atomic number 11, would rather have 10. It wants to get rid of this electron that it has. And lucky for us, it's going to bump into a chlorine atom which has 7 valence electrons. So hopefully you see that by giving away this valence electron to chlorine, now chlorine has 8 around it, which is a very happy place for an atom. And it also has 1 more electron than it does proton, which gives it a negative charge. Now, sodium is going to give up its electron, so now it will have one more positive proton than electron, and that's why it's going to be positive 1 or 1 plus charge. Now, a 1 plus charge and a negative charge of 1 are going to attract each other. So what's going to happen is this is going to form an ionic bond. Okay, we know in science opposites attract, and here we have a positive charge and a negative charge, so these two are going to come together, lock together in an ionic bond. We could also look at barium sulfide, which you see as BAS. Barium's a group 2 element, has 2 valence electrons. Sulfur is a group 16 atom, and it has 6 valence electrons. And hopefully you can see and imagine that barium would like to give up those 2 to sulfur, making sulfur happy, and the loss of 2 by barium makes barium happy. So barium then becomes a 2 plus charge, sulfur is a 2 minus charge, and they're attracted in an ionic bond together. Ionic bonds happen when metals attract nonmetals by this mechanism. The way I like to look at sodium and chlorine is in this this moving example right here. When you first see sodium come into the picture, it has 1 valence electron, and you see it instantly when it bumps into chlorine. It gives up that valence electron to chlorine, and chlorine gains a negative charge, which allows them to stick to each other through an electrostatic attraction. We can also analyze it in terms of atomic structure here. Here's sodium with its 11 protons, 12 neutrons, and it has 11 electrons. But it's going to give up its 11th electron over to the chlorine, and by doing that, it will become positively charged. Chlorine becomes negatively charged, and they stick together through an electrostatic bond or an ionic bond. Ionic compounds are typically found in crystalline form. They are hard and brittle. However, when salts are dissolved, they conduct electricity, which is important biologically. So what happens is these crystals are going to come apart in solution to form positive and negative ions, which is biologically very, very important. We have to have certain levels of these ions to remain healthy. When these ionic compounds come apart, they are also referred to as electrolytes in solution. And we are pretty familiar with this liquid solution of electrolytes here. And this one here, a lot of people don't know what this is, but this is actually a portion of your blood. This is called the plasma. And the plasma contains ions as well. And those ions, like we said, are very, very important to maintain those levels of good health. Okay, so what we're going to look at now is a version of this particular ionic compound breaking down and how that happens. And you can see that surrounding, well, let's just talk about what we find down here in the beaker. In the beaker, you have a pile of salt, and that salt is quickly going away. And the reason why it's going away is because it's being pulled apart by these polar water molecules. If you look in the picture, this is like the blown up corner of that pile of salt. You'll notice that we have what's called a hydration sphere around each of the ions that are being pulled away from the gigantic pile of salt. This is a chloride ion, this is a sodium ion. And you'll notice that there is a special type of arrangement when one of these gets pulled off. Notice there's a connection between all of the white parts of these water molecules here and the chlorine. Why is that? Well, chlorine is negative in charge, and these white parts, these are the hydrogens of water, and they have a partial positive charge. So like we said before, when that happens, they're going to attract one another, and it's going to pull each one off of this pile of salt. Likewise, on this top example here, you have the red part sticking to the sodium ion that got pulled off, because this is the oxygen of water. And oxygen is very electronegative, so that is going to be attracted to the positive ion sodium. Okay, so the summary for ionic compounds is that they are made of metals and nonmetals. We could say they're also made of cations and anions. That's a fancy term for being positively charged and negatively charged. They're often found in a three-dimensional structure called a crystal lattice, which comes apart in solution because most living things have some type of aqueous water component that's going to be very physiologically important. Ionic compounds follow the octet rule, and that is that rule of 8, where everything wants to be happy by having the 8 electrons. So it guides bonding in chemistry. Atoms gain or lose. Now, the other thing that I mentioned earlier is that atoms can share electrons as well in order to achieve a configuration of 8 valence electrons, and that's what we'll get to next. And final note is that hydrogen and helium are different because they haven't yet gained enough electrons to make that magic number 8 happen. They're happy with 2. So hydrogen will comfortably share 2, and so will helium to become stable. So the next type of compound is called a covalent compound, and that's where we said that atoms are going to share electrons in order to make an octet instead of one giving up and one accepting an electron. Now they're going to be shared between 2 atoms to make that octet, or that outer shell of 8 electrons. So let's get through some terminology first, and then we'll be able to proceed. So the smallest unit of a covalent compound is referred to as a molecule. It's 2 or more atoms that are covalently bonded together. A covalent bond is a chemical bond formed from, again, a sharing of valence electrons in order to achieve an octet. So if we take a look at our examples that we see here, here is a hydrogen atom, and it has 1 valence electron. Here's another one, and its valence electron just happens to be on the other side. And if the 2 of them come together, they're able to share the 2 electrons between them, which we show in chemistry as a single dash. That represents a covalent bond. So we said that hydrogen and helium tend to be happy with just 2 electrons, whereas everything else needs 8. So we can see that clearly demonstrated with the case of chlorine. In this chlorine atom right here, we have 1, 2, 3, 4, 5, 6, 7 valence electrons. So we have the same in the other one. It just, the single one happens to be facing a different direction. Now imagine that these 2 chlorine atoms are on a crash course for one another, and they smush into each other, and lo and behold, there is a sharing that's going to take place between this electron here and this electron here. So now if you went ahead and you counted, what you would count out would be 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. By smushing together, each one now has 8 valence electrons in its outer shell. So again, we're going to show the covalent bond as a dash in chemistry. Now, what happens if we mix and match? No problem, because hydrogen just needs 1, and chlorine also just needs 1. And the 2 of them are going to find that 1 electron in each other. So again, they're on a crash course for each other. This one is going to bang into this one, and that's going to give hydrogen its 2 electrons. Here's 1, here's 2, called a bonding pair. And then chlorine is going to make its 8. 1, 2, 3, 4, 5, 6, 7, 8. A couple of other phrase drops in here, vocab drops, is a bonding pair is the shared pair of electrons between 2 atoms, and lone pairs of electrons are ones that are found on the outside of an atom that don't bond with any other atom. So this one has 3 pairs of lone electron, or 3 lone pairs of electrons, you could say. And then again, we'll represent the bonding pair with a dash. Okay, so now that we're familiar with the concept of sharing electrons, we have to bring in the concept of polarity. Polarity reflects an unequal sharing, or a measure of unequal sharing between 2 atoms. So in the case of hydrogen and fluorine, each one of these has its own unique electronegativity. So hydrogen has 1 electron, and its electronegativity is 2.1. Now, how do I know that? Well, if you look in the bottom right-hand corner of a periodic table, what you're going to find is that you're going to see this numerical value that represents electronegativity. It's not on all periodic tables, but it is on the one that I give out to my class, and you can easily find one just by Googling periodic tables and looking at them, and you'll see some with electronegativity listed. Now, fluorine, with its 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. This one actually has a very high amount of electronegativity. This is 4.0. That's as high as the scale goes. Because fluorine is such a small atom and the electrons are so close to the nucleus, it has a very strong pull looking for the 8th electron, so it gives it a value of 2.0. Now, hydrogen with its 2.1 is quite a distance away numerically from it. So what that means is basically we're going to have fluorine as our big electron hog over here, and then we have hydrogen as just having a little bit of pull. Because remember, hydrogen wants to pull one towards itself so it can have two, but fluorine is much stronger in its pull, pulling hydrogen's electron closer to it in order to achieve its 8. And what that does is it's going to produce a partial negative charge on this end of the molecule, and meanwhile, this end of the molecule is having its electron pulled away from it, so it has a positive charge. So imagine if you have negativity pulled away from you, you become more positive. Okay? If we looked at the water molecule, the water molecule has oxygen and 2 hydrogens. So it's like this. And oxygen's electronegativity is 3.5. And hydrogen's, again, is 2.1, and that's for each one. 2.1 there, and 2.1 here. The electronegativity scale, we'll call it ENEG, goes from 0 to 4.0, where 4.0 is the highest electronegativity, and 0, of course, would be the lowest. Now, in a molecule like water, you're going to see that oxygen with its 3.5 value has a much stronger pull on the electrons than these 2 hydrogens here. So what's going to happen is that oxygen becomes our big electron hog, pulling most of the electrons this way. Oxygen is also small, so it's going to have a pretty strong pull on these electrons, and it needs 2 to become stable because oxygen has 6 valence electrons. I should probably put in its lone pairs here so you can kind of imagine what oxygen has around it. Whoops, there's the other one right there. So now by connecting onto 2 H's, we have 2, 4, 6, 8. Remember, the single dashes represent 2 shared electrons. Hydrogen still gets its 2, but in no way is it pulling nearly as strong as the oxygen is. So what that means is that the negative charge is going to be at this end down here, and you're going to have a positive charge here and a positive charge there because these 2 hydrogens are getting their electrons taken away from them. So where would these 2 charges meet if they had to meet somewhere? Well, they'd meet right in the middle. And what that means is that you have a pole that goes down the center of the molecule, the negative end being over here. The positive end being on this side, the negative end being on that side. Now, iodine, I2, has a special case going on with it because it's bonded to itself. Now, iodine has 7 valence electrons because it's a group 17 or a group 7A element from a group called the halogens. And we're going to draw another one right next to it because I2 means that there's 2 of them. So we're going to have 7 valence electrons around this one as well. Now, we saw on a previous page that these 2 can smush towards one another. So if this iodine was on the move and this one was as well, and they're set to bang into each other, what's going to happen are these 2 electrons in the middle are going to be shared. And what you'll wind up with then is you'll have the iodine sharing a pair in the middle, which will replace with a covalent bond. And then we're going to have the lone pairs are still going to be there around the outside. And if we're asked to determine polarity with this molecule, we have to understand that this iodine on the left is 2.5 and this iodine on the right is 2.5. And when you have values for electronegativity, you can also subtract them to find out what the true difference is. Like if we subtracted this hydrogen fluoride, you wind up getting 1.9, which falls into the realm of polar. With the water, 3.5 minus 2.1, we wind up getting 1.4, which falls into the realm of polar. And 2.5 minus 2.5 obviously equals 0, which is considered nonpolar. The way the scale works is kind of like this. If you have 0.0 to 0.4 or 0.5, you wind up having a nonpolar molecule. And it means that the electrons are shared pretty evenly. 0.4 to about 2.1, that kind of falls into the polar realm. And then if you go higher than that, 2.2 to 4.0 in difference of electronegativity, you actually wind up being more ionic than you are polar. So it's sharing so unequally that it completely strips the electron away. So in the case of iodine, what we have here is we have a fairly even sharing of the electrons. They don't seem to be on one side more than the other. And that happens to go with symmetrical molecules. When, I could divide this right down the center here and both sides are identical. And what that means is you typically have a nonpolar molecule when they are symmetrical. You can't cut through a water molecule through every plane and have it look the same, and that is characteristic of a nonpolar molecule. Same thing with the hydrogen fluoride. So you wind up, our last two examples here, hydrogen chloride and oxygen, we could go ahead and we could just take a guess. Since this is hydrogen bonded with a chlorine, this is hydrogen bonded with fluorine, they're both hydrogens bonded with halogens, so that means this is most likely going to be polar as well, just like that molecule. And O2 is just going to be two oxygens, and they actually wind up double bonding to one another. And this one winds up being a lot like our case with iodine. So in that case here, we're going to have a nonpolar molecule, just like the iodine. So why is this important biologically speaking? Well, because polar molecules tend to like other polar molecules, and they have no problem dissolving in aqueous solutions. Nonpolar molecules do not mix well with polar molecules. So we have this saying in chemistry, we say like dissolves like. And if you have a nonpolar substance close to another nonpolar substance, they have no problem mixing. But if one is polar and one is nonpolar, they don't like each other at all. Okay, so let's take a look at how these covalent bonds wind up playing out here. We have two atoms, and notice what happens here with a covalent bond. We have a sharing between the two. This one is nonpolar because our electron cloud, which is out here, is evenly sized. One atom is not pulling any harder on the other one. This would be an example here of a polar covalent bond. As you saw, let me replay that one more time. When the atom comes in, you see that the atom on the right has a much greater pull on the electrons. So this is going to be the negative end of the molecule. That's going to be the positive, like two almost like a magnet with two poles. And then the ionic bond was when we had one atom giving up an electron and the other one taking it. And when that happens, the one that gets it taken from it will wind up being your positive ion. The one that takes the electron on is your negative ion. And again, there's special names for these. That's an anion, and a positively charged ion is called a cation. Okay? And Kevin Patton, I fed the lions with your slide. Thank you. Okay, so here we see a particular enzyme. It's called a lysozyme. And you can see that water is thoroughly attracted to the outside. If you take a look at all these little tiny water molecules right here, you see that there's an interaction between them and the part of the protein that happens to be charged a specific way. So water will line up with the opposite charge and then stick to this enzyme. So the third type of bonding is called hydrogen bonding. And hydrogen bonds are the attractions between hydrogen atoms and the lone pairs of our three most electronegative elements, nitrogen, oxygen, and fluorine. They are the strongest type of intermolecular forces because they exist, because the molecules they exist between are very polar. So if we're talking about covalent bonds and ionic bonds, typically we're talking about intramolecular forces, things that hold molecules together, or formula units of ionic compounds. But here we have an intermolecular force that occurs between two particular molecules in the same sample. So they may be attracted to each other because they have huge electronegativity differences at the moment which they touch one another, or come close to touching each other. So if we take a look at these examples down here, you can see that we have a water molecule right here, and here we have an ammonia molecule, and here we have a hydrofluoric acid molecule. Now, the way this is going to work is that if there is another water molecule in the generalized area, what's going to happen is it's going to arrange itself in a particular way where the hydrogen is going to be attracted by way of a hydrogen bond, in this case, to this oxygen. So it's two distinct molecules that are attracted to each other because of it. If we had an ammonia molecule, and this one was coming in this way, its direction of flow is towards this other molecule, there's going to be a attraction between this positively charged hydrogen and this negatively charged nitrogen, and that is considered our hydrogen bond in this example. So here's our hydrogen bond in there. And then hydrogen fluoride, same thing. If H is bonded to F and it comes in contact with this fluorine, there's going to be an attraction here as well. And those are what hydrogen bonds are. They're attractions between molecules. Ionic bonds and covalent bonds are stronger in terms of relative strength, but again, those are intramolecular and not intermolecular forces. Okay, so water's ability to hydrogen bond is very important biologically because there's so many things within living organisms that have the chance to be attracted to water briefly and let go. So here's just a few different looks at hydrogen bonds in water. This is as basic as it gets when you have two molecules that are connected to each other by way of the hydrogen bond. And in this one here, notice that they all seem to be lined up and facing the same direction. This is a special case for water, and the state of matter that this is in is actually the solid state. So this is how they'll line up. And these hydrogen bonds in the solid state actually are spread a little bit further than that in a liquid state, and that allows them to have a little bit less density, which gives water the ability to float on a surface instead of sinking to the bottom. So the colder that water gets, the less dense it becomes, and that's why you can walk on frozen ponds and lakes in the winter time, because the part closest to the atmosphere has frozen solid, and now it acts like an insulator, insulating the liquid water underneath it from those harsh cold temperatures. So if we're looking at some water molecules, if we could shrink ourselves down and go scuba diving, shrink ourselves down to submicroscopic size, we might see water look like this. And these hydrogen bonds that form, they are instantaneous. They will release one moment after establishing a bond because another water molecule is going to strike it. And if we put some more into the mix, we can imagine what it would be like underwater. It'd be a non-stop barrage of water molecules slamming into each other, bouncing off at various angles. So it's very temporary, on the order of microseconds, nanoseconds that those attractions exist. But collectively, there is an attraction because there are so many molecules together, and we see that in the surface of water. It's giving us surface tension. So I hope the chemistry of biology is a little bit easier to understand. Of course, there's no substitute for just popping that book open and reading as well. So make sure you do your readings to glue the lecture together. And sometimes it takes 2-3 times to really start understanding the ideas. And of course, it takes a lot of practice as well. So do as many problems as you can. Just to kind of review just a little bit, the 3 types of bonds that we saw today were ionic, covalent, and then the hydrogen bond. Ionic and covalent were intramolecular forces holding together molecules and formula units of ionic compounds. And with hydrogen bonding, we're now talking about different molecules being attracted to each other, which we call intermolecular forces. So to continue this lecture, go ahead and look at water and its biological importance. You'll find that in my video vault, and it's kind of just a continuation of what you've been seeing here, and it goes more into depth about water. I'll see you next time.